Okay, so it is a good time to show some examples for the merkle-damgard construction as the compression function. So for the compression function, the merkle-damgard construction, here, let me remind you the picture here. Here, the F compression function can be MD4, MD5, SHA-1, SHA-2. So here, we will talk about them. So let's start with some broken old hash functions, and let's start with MD4. So it was developed by Ronald Rivers in 1990. Block size is 512 bits. So your messages are divided into 512 bits blocks. The message digest length n is 128 bits. So as you can see, for the collision, we need to perform 2 to the 64 operations, which is not much of a problem nowadays. Okay. So this is a picture of a single round, and the number of rounds are 48. So you have to repeat this process 48 times. As I mentioned, this is a merkle-damgard type construction. ABC in this picture, ABCD, are state words of 32 bits. So all of these words or lines represent 32 bits, okay? So it starts like this. So initially you put IV here, okay? Perform these operations. There's an F function which just uses some logic operations. We will see them when we talk about the other hash functions. But the important thing is that here you have modular addition. This means that you are adding 32-bit values like a normal addition, but modulo to the 32. And actually the message is fed from here as 32 bits per round, okay? So you don't write your message here. This is filled with IV. But every round you feed your message from here, 32 bits per round. There is a constant here, which is specified in the standards. And there are some rotation to the left. And like a Feistel cipher, this goes here, this goes here, and so on. This is a single round, and you repeat it 48 times. So let's talk about the security. Generating a collision takes a few microseconds. So as you can see, it is badly broken. Okay. There are some pre-image attacks which breaks the system by performing 2 to the 95 operations. Of course, these are academically known results. Maybe agencies have better attacks. We don't know them. Okay. It was IETF standard hash function defined in RFC 1320 and retired in 2011. Think how late this is. Okay. This is why it is important to have strong crypto. If you have something bad and if it is broken, it takes years to replace them. So this design influenced later designs like MD5, SHA-1, and RIPE-MD, also SHA-2. So let's look at MD5. It is again developed by Ronald Rivers 1 year later to replace MD4. The picture is almost identical. As you can see, there's an extra addition here. And another change is number of rounds now is not 48, but it is 64. Okay. This is just to strengthen the algorithm, but the thing is that we can still break it. So in MD4, I haven't mentioned what this FI function is. Here, I explain it. So since this is 64 rounds, every 16 rounds, this FI turns into F, G, H, or I, okay? So in each case, as you can see, the operations are just logical operations. So you know that this is XOR operation, this is AND, this is OR, and this is NOT symbol, okay? So basic logical operation. So as you can see, this is a super fast algorithm. You don't do much actually. Basic arithmetic logical operations. So now collision resistance, again, we can break it, but not in microseconds, but maybe in milliseconds, right? Because generating a collision requires around 2 to the 18 operations. This is less than a second on any regular computer. Pre-image resistance, there are still attacks better than exhaustive search. In 2004, it was shown how to create a pair of files that share the same MD5 checksum. So this is bad, right? Actually, you can break cloud services if they had used MD5, because you would put two different files and they would think that it was the same. Okay. In 2005, Lanstra, Wang, and Weger demonstrated construction of two X509 certificates with different public keys and the same MD5 hash value. So we haven't seen digital signatures yet, but there we use certificates, and If you sign things as the hash of MD5, they show you how to they demonstrate how to two certificates with different public keys and have the same MD5 hash value. Later on in 2008, it is shown how to fake SSL certificate validity. So certificate authorities should stop using MD5. This was said in 2008. But then this thing happened. In 2012, there was a very famous malware, maybe one of the first famous that affected many countries. So the authors of Flame malware used an MD5 collision to forge a Windows code signing certificate. Okay. You can see that, you know, the algorithms are broken years ago, but it affects everybody in 2012. So this is why when a cryptographer says you shouldn't use an algorithm, you shouldn't use it. Okay, that's for sure. This is the same thing happens right now. I'm saying that SHA-1 is broken and you shouldn't be using it. But people say that, we will see in a minute, that those attacks are not that practical. So why worry now? But a similar thing will happen in a few years, like the malware, Flame malware. Okay. So try to avoid using broken algorithms. So here's an MD5 collision example. The X1 here is a one message block, 512 bits. X2 is another message. They are different, but they give the same MD5 output. So they are collision. So difference here are shown in red. Okay, the black parts are identical. But here, as you can see, it is 7. Here it is F. In hexadecimal, you see that the leftmost bit is 0 here and it is 1 here. So you are introducing a small difference. So you can guess that this is a differential attack to find a collision. Okay, so you simply replace FE bits here, flip them, and it causes a collision. Of course, it doesn't work for every input, but you have to try many. So this is why it requires around 2 to the 18 operations to find such a collision. This is just a single example. You can produce thousands of them in seconds, okay? So let's move on to something recently broken, let's say, because people were still using it in the 5 or 7 years ago. So this is SHA-1. It looks similar to MD4 and MD5. But the difference is that now it is not developed by Ronald Rivest, it is developed by NSA, okay? So actually, they published something in 1993, and then they modified it. So this is why we call it SHA-1, and that previous version is SHA-0, okay? And the modification was to adding a single bitwise rotation. I think it was this part they added. And this addition made in 1995. So this new algorithm is renamed as SHA-1. But this is important because normally you don't give you the name 1 to your first design, right? This is why it is called SHA-1. Before SHA-2, we were saying this SHA-1 or something like that, okay? So it looks like MD5, but as you can see now, the message digest length is increased, 160 bits. So you add 32 bits more. This is why in the previous pictures, we had words from A to D. Now we had another word E to make it 160 bits here, okay? Number of runs increased again to make it more resistant to differential attacks. And the rest is almost identical, okay? So here's an example. I think this is from NIST documents. Here we show how you calculate the hash of an input. So input here is just one block. Actually, it is very small, 3 letters ABC, but this is not hexadecimal, okay? From your keyboard, you are pressing ASCII characters ABC, okay? So what happens is as follows. Since the block size is 512 bits, we have to perform some padding. So A, B, and C in the ASCII table, you will realize that they represent 61, 62, and 63 in the hexadecimal notation. Then you perform the padding, 1 bit of 1, and you fill the rest with zeros. Until here you write the size of your message. Here it is 3 bytes, 24 bits. So you write it in hexadecimal. This is to prevent some length extension attacks, actually. Okay, so IV is here. So you fill the words with this. So if I go back, you write it here. Then you start feeding your message from here. These are the block contents. And these will be the outputs of your rounds. Okay, A, B, C, D, E values. Okay, You go from here. Since it is 80 rounds, you continue this. And at the end, when you finally have the A, B, C, D, E values, you write these values here. And these are your IV. You add them. This is not an XOR addition, modulo 32 bits. And you end up with this. So this is your hash. So if you create a TXT document, a text document on Windows, write ABC to it, save it, then calculate the hash of that file, you will see that the output will be this. Okay. So this is the test vectors for this. Again, SHA-1 is broken because if you think about it, a brute force attack will require 2 to the 80 operations to break the collision resistance, right? Due to birthday paradox, because message digest length is 160 bits. If you divide it by 2, you will require 2 to the 80 operations to find a collision. But years ago, people realized that, I think it was Wang that found the attack, saying that you can actually find collisions if you perform 2 to the 63 operations. So at the time, people analyzed this paper and realized that the paper is correct. Yes, you can find it. But performing this many operations and storing a lot of the results on the memory was not practical. So for a very long time, people couldn't come up with a practical collision. So in theory, we knew that there was collisions. It was easy to find, but nobody had the computational power to try it until a few years ago. I will show the examples. But even in gambling web pages, there were gambling saying that, okay, this year there will be a SHA-1 collision or not. You could gamble on this stuff. But this collision resistance, this attack works for SHA-1, but for SHA-0, you can find the collision by performing many, many less operations. This is why we understand why NSA actually added an additional rotation operation here, okay? Just to make these things complicated. So browser of Microsoft, Google, Mozilla stopped accepting SHA-1 SSL certificates by 2017. Maybe you remember those days. All of a sudden, the web pages you visited regularly now, your browser starts giving some red error saying that, are you sure it might not be secure and so on. It was because they were using SHA-1 SSL certificates, okay? So let's look at the history of the collisions. So in 2015, the first not full collision, but free start collision was provided. So here you see the IV, you see the message M1. And if you change the IV and the message like this, as you can see, some parts are identical, but there are small changes here. Again, this is a differential attack. And both of them provides the same SHA-1 hash value. So this was found by Stevens et al. And they actually used 64 GPUs, GTX 970. Those are really efficient at the time. And they kind of perform 2 to the 57 SHA-1 evaluations. So a free start collision breaks the inner layer of SHA-1, does not directly translate into a collision on the full SHA-1, because the attacker is not able to choose the initial internal state, right? Because you are not allowed to change the IV actually. It is fixed on the standardization document. So here, Mark Stevens is trying to tell that if I can find this, and if I had more GPUs, I could find a full collision to SHA-1. Okay, this was his claim, and he was right. Because after this paper, Google said to Mark Stevens that, okay, we have a lot of GPUs. Just modify your code, and let's find a collision for SHA-1. So Mark Stevens asked how many GPUs you have. They said that we cannot tell you. You will simply write the code, give it to us, we will run it, and we will give you the result. So for this reason, initially there were some problems because without knowing the hardware infrastructure, it was hard to code. But then they did it. And in 2017, Mark Stevens and people at Google actually came up with a collision. So this time, the strange thing is that this is 2 message block collision. Okay, so this was the first block of the first message, second block of the first message, and this is at the end is your hash value. And here you are using different message blocks, but you end up with the same hash value. This one equals to this one. Okay, and these red and blue parts are the parts where you have differences. Okay. Okay, so it is really broken, so there's no need to insist on using this. Okay. RIPE-MD was developed by Daubertin, Bosselaers, and Prenel. As you can see, this one was designed by academicians, not NSA. So it looks very similar to SHA-1. The message digest length, we can choose 160 like SHA-1. But the operations are a little bit different, okay? The good thing is that nobody could come up with a collision attack so far. So if you want short hash outputs, instead of using SHA-1, you can use RIPE-MD 160. Okay. So RIPE-MD 160 is the only remaining 160-bit digest size hash function that has not been broken yet. It was developed in the open academic community in contrast to the NSA design SHA-1 and SHA-2. And actually, this is why Bitcoin uses RIPE-MD 160. Okay. When you create an account, first it is compressed with SHA-256, then RIPE-MD 160, so it becomes smaller. Okay. SHA-1 source codes are already in Bitcoin, but never used for generating accounts or anything like that. Okay. SHA-2, the second non-broken algorithm we have. This was developed by NSA, first published in 2001. As you can see, now we have larger message digest length. So most used one is 256 because we prefer 128-bit security for current, computational power. We always suggest 128-bit security, and this provides it due to birthday paradox. But if you want military-grade security, you should stick to 512. So these are used. I wasn't expecting anybody to use 384, but you can see many web pages where the hashing is done with this on the certificates, okay? Probably somebody told me that there was an error in the 512-bit implementation of some company, so they used this one, and probably it got stuck there. So currently there is no reason to, choose it. Anyway, number of runs depends on the message digest length. It is again merkle-damgard. As you can see, we have more words just to make it 256 bits. Now we have more functions, majority function here, sigma 0, sigma 1, etc. But again, they are logical operations like this. So sigma 0 and sigma 1, actually just rotation and XOR. And these are very similar to the ones we had for MD4 and MD5 and SHA-1, okay? So collision resistance, nobody could come up with a full attack, but there were some pseudo collision attacks against 46 rounds of SHA-256 out of, 64. And preimage attack, as far as I know, there is a 2011 attack that breaks preimage resistance for 57 out of 80 rounds of SHA-512 and 52 out of 64 rounds of SHA-256. So it is secure. So this is why we are using it all the time. But as you can see, the previous ones are broken. This is why we actually had a competition called SHA-3 to have a backup plan. Okay.